Okay, everyone, let's pick up where we left off last time, sort of a review where we were in talking about electrons, this fourth unit of study. We had begun with the idea that electrons placed around the nucleus of an atom are arranged in energy levels. And these energy levels radiate out with regards to distance from the nucleus of the atom. And notice that the distance between the energy levels decreases as we increase in energy level, and ultimately that ends up in overlap of energy levels starting at the third and the fourth energy level right here, where we haven't quite finished the third energy level before we pick up that fourth energy level. That has direct connotations for the shape of the periodic table, some of which we looked at last time. With this information in hand, we were able to come up with a couple of new languages for describing the way electrons are stacked around the nucleus of an atom, both electron configuration as well as drawing orbital diagrams. And lastly, what we left with was sort of a shorthand methodology of describing electron configuration. I should say only electron configuration and not orbital diagrams, but through the use of noble gas cores. So either way, we have different elements can be written out in the full manner of what we see here, or in an abbreviated manner. Similarly, a couple of examples here that we looked at. So to move on here, we are going to now distinguish between types of electrons which populate the area around the nucleus of a particular atom. There's actually two kinds of electrons. There are what are called core electrons and valence electrons. We're going to address what valence electrons are. Now, a couple of important points here. Once a noble gas core has been achieved, as we're reading the periodic table like lines on the pages of a book, once we pass the end of a row, that is the end of an energy level. That's also a noble gas core. As we continue past the end of that energy level, those electrons which preceded it up to and including that noble gas core are not available for chemical reaction anymore. They are locked away. They're essentially useless. If we have electrons and they're not used for chemical reactions, we have no use for them in chemistry. And specifically, I keep going back to this, but it's important. Only electrons in the S and P block are relevant to the model we're putting across here, not within the transition elements or the D block, if you will. So having said that, we can make the statement that only S and P electrons above a noble gas core can participate in chemical bonding. So let's take a look at that. Again, so what I've done here on the very bottom is I've cut off the first three top rows of the periodic table, just in order to give an example here of the electron configuration of silicon, as we see here. Silicon, if we look on the periodic table, there it is, and we can methodically move across the rows on the periodic table to come up with its electron configuration. So we see then, and what we would ultimately get here is this piece right here: 1s2, 2s2, 2p6, 3s2, 3p2. And that's, again, if we look down at the periodic table here, we would be able to use the periodic table in order to assist us in getting there. Now notice in blue here in this diagram, these are considered the core electrons. Why? Well, because they represent the preceding noble gas core of neon. And it's only the electrons in the the currently open energy level that are open for chemical bonding. Those are the valence electrons. So now we see a difference between core electrons and valence electrons. All electrons are not the same with respect to how they whether they can react in chemical reactions. So over here now at neon, that closes us off with the core electrons, and then we start into the next row. So we got 3s2, 3p2 till we get to silicon. Notice these are the ones in yellow up here. Our valence electrons are in the currently open energy level. The currently open energy level. So that is ultimately important. So how do we tell what our valence electrons are? Well, first of all, we could write our electron configuration out using our noble gas core terminology with neon in brackets here, and then the currently open energy level. Those are those 4 electrons, 1, 2, 3, 4, are our valence electrons. How do you tell how many valence electrons a particular element has? Well, look at what we were doing. We were going straight across, and we would count across the periodic table. For instance, for silicon, how many elements do we go through? Well, 1, there's sodium, 2, magnesium, 3, aluminum, and 4 into silicon. There are 4 valence electrons for silicon. It's all about counting over from the row that particular element lies in. Remember, only in the S block and the P block are we talking about. If there happen to be D electrons in there, we would disregard them for the purposes of this model. So we have defined valence electrons as really the only electrons that are important in an atom, because this is a chemistry course. We want to deal with the electrons that participate in chemical reactions. So there is a shorthand way of describing an element with showing just their valence electrons and disregarding any core electrons that they may have. Again, we have this familiar piece of our first top 3 rows of the periodic table that I've cleaved out, because those are the ones that are important to this argument. And let's take a look at the second row on the periodic table, and we're going to move across methodically on that second row, looking at a way of expressing our valence electrons in something that's called an electron dot model, or a Lewis symbol of that particular elemental structure. So we'll start here. How would we describe just the valence electron configuration of our first element here, that of lithium? Well, ultimately, what we do is we draw the chemical symbol for lithium, and we put a dot next to it, which represents the 1 valence electron that lithium has. Why 1 valence electron? Well, counting over in that row, it's the first element in that row is going to have 1 valence electron. Now, electrons are placed around this chemical symbol singly first. So one side we'll place one electron on one side, then go to another, it doesn't matter which side, and then another, and then another until that's filled up, and then we'll double up electrons. I'll show you what that means as we progress across this row on the periodic table. But let's look at the next electron, or the next element rather, and that would be that would be beryllium. That would be the next one in the row. How many valence electrons? Well, that would be 2, and we express those placing 2 dots around there. Notice it doesn't matter which side we put these electrons on. I could, if I wanted to, I could have this electron dot up here on beryllium instead of across. That's fine, but as long as they're not populating the same side, that's okay. So that would be a Lewis dot symbol representation of beryllium. Moving across some empty space here to the next one, boron, with 3 valence electrons, because it's the third element over in a row, and this is the way we would express that. See, as you can see, immediately we see what the element is and how many valence electrons it has. Boron would have 3. Next one over is carbon in that row, 4 valence electrons. Now notice we've now filled up all 4 sides of this elemental symbol. So when we go to the next one, which is nitrogen, we now have to start doubling up our electrons, and we will get something like this with 5 valence electrons. So notice we have a distinction now between the electron structure on nitrogen. Let's take a closer look at this. We can distinguish between the way the electrons are arranged. Single electrons, and this is going to be important for reactivity, single electrons around an elemental symbol in an electron dot structure or Lewis structure, single ones are unpaired electrons. So we consider them unpaired electrons. Where they're doubled up is considered a lone electron pair. With respect to reactivity, there's a big difference there, and especially when we talk about reactivity, we're going to be talking about chemical bonding. So it's important that we can look at a Lewis dot structure of an element and see the difference between them, between unpaired electrons and lone electron pairs. All right, moving along, next to oxygen with 6 valence electrons. Again, we would have to double up one of those singles. So now we have 2 unpaired electrons and 2 lone electron pairs. Moving over one more to fluorine, we would just add another electron to have 7 valence electrons. Now we have 3 lone electron pairs and 1 unpaired electron. Very last, to neon, this is the end of a row, the end of an energy level, and also that blocks off all those electrons from reactivity once we start the next row beyond it. So neon, we would add one more electron, and look at that, a full octet. We can count 8 electrons around it. Around neon, they're all lone electron pairs. And we know that the noble gases have a very special stability to them. And so this noble gas configuration of electrons is quite desirable, as we learned in the last lecture. Many elements try to become isoelectronic with that noble gas to attain a noble gas configuration, even if they form ions in the process. So let's look at what we did here. We went all the way across the second row in the periodic table, and we were able to express the Lewis dot structure for each of these elements, this shorthand way of doing it. But what happens if we move to the next row down? The next row now it starts with sodium, the third row, but as we move across the periodic table in this row, we would find that the electron dot structure is exactly the same. It is identical. So let's if we took out all of the chemical symbols of our electron dot structures up top and replace them with the ones just below them, look at what we have here. We have identical Lewis structures, identical, between, say, lithium and sodium, between beryllium and magnesium, between fluorine and chlorine, between neon and argon, between all of them. So it shouldn't come as a surprise that, for instance, fluorine and chlorine are right in the same vertical column, right on top of one another. Oxygen and sulfur are right on top of one another, as are all of them. And what was that term that we had used previously, that term of periodicity, similar reactivity in elements in the same vertical column of the periodic table. Why are these elements, why do they have similar reactivity? Because they have identical Lewis electron structure. Similar reactivity is derived from identical Lewis electron dot structure. So put another way, this brings us back to these chemical families that we were talking about, some of which are shown here. Not all, but some of them. We have our noble gases. Why do they all react, or rather not react, similarly? Same with the halogens. Why is that? Why do they all tend to pick up one electron in chemical reactions? Alkaline earth metals? Why do they tend to lose 2 electrons in chemical reactions? What is up with that similarity of reactivity, that similarity of electron flow? It's all to do with elements in the same vertical column of the periodic table having identical Lewis electron dot structure. Now, I haven't shown all of them here, but indeed, if you remember what I said before, this similarity in reactivity, this periodicity, is more prevalent towards columns at the periphery of the periodic table. Way over noble gases and halogens on one side, alkali metals and alkaline earths on the other side. And certainly, you know, other columns moving forward have that periodicity to them, but it's really, as we move out to the outward columns on the periodic table, it really is a slam dunk sort of thing. It's much more prevalent than it would be in columns as we approach the center of the periodic table, not the center, because that is the D block, and the D block, as we said, is governed by a different type of reactivity model, which we're not going to go into here. But you know, as we move towards the center of the P block, well, we get some sort of that similar reactivity, but not as intense as those peripheral columns at the periodic table. This similarity in reactivity becomes quite glaring when we look at the electron configurations of elements in the same vertical column of the periodic table. We covered this before, but let's look at some alkali metals. That first column on the left of the periodic table, lithium, sodium, and potassium. We can really see this periodicity, that elements in the same vertical column of the periodic table tending to have similar reactivity, is because they have not similar, but identical valence electron structure. Let's take a look at the electron configurations of these elements. And while the electron configurations themselves are quite different, all that difference is in the core electrons of these elements, which are by definition non-reactive, and we don't care about them. But it is indeed in the valence electron structure in which they're identical. All of them have that S1 identical valence electron structure. That is what we depicted in the Lewis structures of elements, that one dot, if you will, and it is the basis of the similarity in reactivity, in this case, between lithium, sodium, and potassium. This idea can be extended to the alkaline earths, the halogens, and you know, oxygen, sulfur, all those different columns, and so on. We would hopefully remember this slide from the prior unit of study, the predictable ions formed from various elements within the periodic table. And we find that elements within the same vertical column in the periodic table tend to form the same ions. We saw this before. And we're going to develop a model now to describe exactly why that is. Now, the first thing I'd like to take a look at here is the fact that, remember, our noble gases here are the only ones that don't form ions. Their electron structure is, they're happy the way they are. Thus, this what is called a noble gas configuration is highly desirable. Indeed, it is a very, very stable electron configuration, which all of the other elements that we see next to it or nearby want to emulate. So this bullet point down here begins our journey. This predictable ion formation, and remember, this is within the S block and the P block. The transition elements form various charges, meaning they're not described by our model right here. So remember, it's just the S block and the P block of the periodic table. In any event, predictable ion formation within the S block and the P block, it centers around the desire for these neutral atoms of the elements to become, fancy science word again coming at you, isoelectronic with the nearest noble gas to it, the nearest noble gas. So not the one that preceded it, but whichever one is closer. And let's take a look at how that might happen on the next slide. So to start our demonstration here, let's look at that first column on the periodic table, our alkali metals. We've seen this series before. There's a few of our alkali metals in here: lithium, sodium, potassium. And over right next to it are the electron configurations of each of these elements. We looked at this before, and we found that the only electrons that matter are the valence electrons. The core electrons which precede them, as we see over to the left in black, don't matter. Why? Because they don't participate in chemical reactions. It is only those valence electrons in purple here that matter. And we found that each of them has an S1. It has one valence electron. If we looked at a Lewis structure, each of the lithium, sodium, and potassium would have that one dot associated with it. So what does it do with that one dot? Alkali metals, as seen in this bullet point, in this case, they prefer always to lose one electron. Now, why is that? When we lose one electron, we become singly positively charged. Why one electron? One electron is lost because by losing one electron, it becomes isoelectronic with the noble gas, in this case, which just preceded it, because that noble gas is closer. Let's look at this. Lithium. Here is our electron configuration. If I lost this valence electron, what would I be isoelectronic with? Well, that is the electron configuration of helium. Great, that's a noble gas. Let's be isoelectronic with it. So lithium, with its one electron, loses that electron to become singly positively charged, and that's okay, because now it is isoelectronic with the noble gas helium. It prefers to be that way. Typically, a neutral lithium atom is uncomfortable compared to a singly positively charged lithium ion, which is much more stable. Now we can do the exact same thing now if we look down at the next one, at sodium right here. Sodium, again, has one valence electron, and if it loses that one valence electron, it becomes singly positively charged sodium. That is isoelectronic with neon. Well, let's take a look. It loses this S1 electron, that one, and if we look on the periodic table, if we work this out, this is the electron configuration for neon, another noble gas. It doesn't matter which noble gas it is, it has a noble gas configuration. So this sodium plus cation is very, very happy because it is isoelectronic with a noble gas, in this case, neon. Let's move on. The next one down, this gets repetitive. Potassium. If we look at our electron configuration of potassium, well, here it is. The valence electron, there's one valence electron right here. And if we lose that one valence electron, what do we have left? Well, we have, and if we looked at this, what's our core electron structure right now? If we worked it out, we would find that that's isoelectronic with argon, yet another noble gas. So it is going from a neutral atom of sodium to a singly positively charged ion of sodium is a very stabilizing process, and thus it will happen spontaneously and indeed very vigorously if we, in chemical reactions, we would find this. So now let's go back and look at, or go back to the periodic table and look at different columns within it. We just looked at the alkali metals, that column that is all the way over on the left of the periodic table. Let's move it in one to the alkaline earth elements, and we'll take a look at okay, here is a periodic table for checking our work here. We'll move over one. this column is our alkaline earth elements. Notice we just finished up our a few examples of our alkali metals, and we found out, well, why do alkali metals all tend to lose one and only one electron in chemical reactions? Well, because they become isoelectronic with the noble gas which preceded it. However, we are going to look at the alkaline earth elements now, and this would be a few of within this column right here, not all of them, but a few of them. And let's look at how their valence electron structure reacts or acts to become isoelectronic with a noble gas which is closest to it. So here are a few representative alkaline earth metals, and let's look at these. We have beryllium, magnesium, and calcium. Now we find that alkaline earth metals don't lose one electron in chemical reactions to become singly positively charged. They always lose two electrons in chemical reactions to become doubly positively charged. Why might that be? Well, if we look at this, if we have, say, beryllium, here's beryllium, and if it loses one electron, it becomes isoelectronic with lithium. That doesn't help it. It has to lose one more electron to become isoelectronic with helium, that one that preceded it. It is two out from helium, so that is why it has to lose two electrons. Let's see how this works from the standpoint of a neutral atom losing those electrons. Here we go. Now look over on the left-hand side here, and we find immediately that beryllium, magnesium, and calcium all have identical Lewis electron dot structure, meaning they have two valence electrons. They're going to lose those two valence electrons, as I said before, in each case to become doubly positively charged. Notice they're always two electrons going away, and we're becoming doubly positively charged ions. And that is a very stabilizing event. Why? Because they become isoelectronic in that doubly positive state with a noble gas. Beryllium is then isoelectronic with helium, which we showed you. Magnesium becomes isoelectronic with neon. Calcium becomes isoelectronic with argon. In each of these cases, we lose the requisite number of electrons to become isoelectronic with the closest noble gas to it, in this case, the one which preceded it. Let's move to the next column over, the last one in the metals we're going to be looking at, and the major one in this case is aluminum over here. We found that aluminum in this case, that typically makes +3 cations. That would mean aluminum, a neutral atom of aluminum, has to lose 3 electrons in chemical reactions. Well, let's take a look at why might this be. Well, here's aluminum, and if I lose 1 electron, I am magnesium. If I lose 2 electrons, I am isoelectronic with sodium. If I lose 3 electrons, I am isoelectronic with neon. Always getting back to that noble gas configuration. And here it is over on the left-hand side. Aluminum, we can immediately tell how many we're going to be losing in case of this metal, because it has 3 valence electrons. 3 valence electrons. So those 3 valence electrons are lost, and we become, as we said before, isoelectronic with neon. Fair enough. This works out pretty well. Let's now move over to the other side of the periodic table. Let's look at, I believe we're going to be looking at our halogens. Our halogens here. And our halogens are fluorine, chlorine, bromine, iodine. It's all the same. Now, halogens have 7 electrons in their valence structure. How do I know that? I count over in that row. The halogen is going to be the 7th over, as long as I disregard the D block, which we see here. We're only counting over within the S and the P blocks right there. 7 valence electrons. Now, given our model before, we could give up 7 electrons for fluorine. 1, 2, 3, 4, 5, 6, and then 7 to become isoelectronic with neon, that's a lot of work. Now, the reason that fluorine, in this case, picks up one electron is because it does not matter which noble gas we become isoelectronic with. In the case of fluorine, and indeed any halogen, if I pick up one electron rather than giving up 7, I am isoelectronic with neon, that noble gas. Chlorine, picking up one electron, becomes isoelectronic with argon. Bromine, isoelectronic with krypton. Iodine, isoelectronic with xenon. So we've gone the other way because it's easier. And here we go. See, we see this, our Lewis electron structure of each of these halogens here is identical. It is identical. So if you can see these 7 valence electrons around the halogens, if we pick up one more, look at that. It's going to be a nice octet around it. That is a noble gas configuration, and indeed isoelectronic with those noble gases which we described before. The upshot, of course, is it becomes charged, singly negatively charged on each of these, but that's okay. That's a fine trade-off because these negatively charged halogen ions now are all isoelectronic with a noble gas. This can be done with virtually or many of the same columns within the periodic table. If we move over a column to the left, over on the right-hand side of the periodic table, now we got oxygen, sulfur, and selenium. Well, what might we expect to be the easiest mode of movement here? Well, how about oxygen? I can pick up not 1, but 2 electrons to become doubly negatively charged. Why? Because that puts me isoelectronic with, again, with a noble gas, in this case, neon. So it's all about keeping up with the Joneses here. Let's look at that row here. I've got oxygen, sulfur, and selenium, all with 6 valence electrons. That is uncomfortable for them. They'd rather have 8, an octet, meaning a noble gas configuration. So if we look at, in this case, for oxygen, we get 2 electrons coming in. They pick up 2 electrons to become O2-. But look at that valence structure. That is a valence structure of a noble gas configuration. Sulfur right below it, it's exactly the same. Picks up 2 electrons to become S2-. Selenium picks up 2 electrons to become Se2-. Why? To get that nice juicy octet, very stabilizing. Moving even over one more column in the periodic table, nitrogen and phosphorus, well, we can see that as well. Nitrogen and phosphorus each have identical Lewis structure, that of 5 valence electrons shown here, and we're able to then pick up, so if we have 5 valence electrons, we have to pick up 3. Why 3? To make 8, that octet. And in so doing, we get triply negatively charged anions, N3- and P3-. Why 3-? Because it's only by picking up those 3 electrons that we're ultimately able to become isoelectronic with the noble gas, in this case, which is closest to it. So we're going to take a little bit of a detour here now that we've understood how electrons react, what the model is, which allows to form ions and so forth. And we're going to look at since we're talking about electrons in this unit of study, and electrons carry out the basis of chemical reactivity, we're going to start looking at reactivity trends in the periodic table. So thus, if we think about the reactivity of elements, and that's all based upon electrons, we find that it's not a staggered regimented approach, but the electron reactivity is actually a continuum. It increases or decreases within a row or within a column on the periodic table. We have gradations, not sort of a yes-no sort of thing with regards to reactivity. it's a continuum. So there's many ways we could explore this continuum of reactivity. There's a large number of trends within the periodic table. We'll look at three representative ones, but just understanding that there are more of them. The first one we're going to look at is metallic character as trends within a row or a column. We'll talk about what that means. Also, first ionization energy as an example. And finally, atomic size. We will cover each of these separately and explain them as we go through the following slides. So our first trend in the periodic table we are labeling as metallic character. Now, what does character ultimately mean? Well, if you remember from a previous unit of study, we were able to, if we were to look at the periodic table, we had this sort of stair-step line, which we see right here, which separates the metals from the non-metals. If we are on this side of that stair-step line, we're non-metals, and if we're on this side of the stair-step line, we are indeed metals. However, if we look at the concept of a metal, we really have an increase or a decrease in what is considered metallic character. Remember, we put out some examples of what makes a metal a metal. Metals tend to lose electrons in chemical reactions. Metals tend to conduct electricity, with the nonmetals doing the opposite, gaining electrons in chemical reactions and acting as insulators as opposed to conductors of electricity. But if we look at this concept of character within, say, a vertical column of the periodic table or a row of the periodic table, any column, any row, really, we would be able to see gradations in type of character. Let me give an example, and we'll look at the alkali metals here. What if I were to say, all right, I have sodium and rubidium here. What can we say about them? Well, you'd say that they're both metals. But I would say to you that one of these is more of a metal, has more metallic character than the other, even though they're both considered metals. For instance, if we go in this with regards to a row in the periodic table, if I had, say, potassium, which is a metal, and chromium, which is also a metal, which they're both considered metals, but one would have more metallic character, one would have less metallic character. Okay, so what's the trend? We have these trend arrows on the periodic table, which says that metallic character increases as we go down a column, any column in the periodic table. So we would find that if metallic character increases between sodium and rubidium, rubidium has more metallic character than sodium because of that trend arrow that we saw last time. As we go across any row in the periodic table, metallic character decreases. So if we had our potassium versus our chromium here, we would be able, since metallic character decreases as we go left to right across the periodic table, we could say that potassium has more metallic character than does chromium because of that trend in the periodic table. Our next trend in the periodic table is called first ionization energy. By definition, the first ionization energy is the energy required to remove one electron from a neutral atom of an element. Some are easier, some are more difficult. So we have trends within the periodic table, and indeed any vertical column or any horizontal row will do. So let's look at these trend arrows here. As we go down a column in the periodic table, the ionization energy decreases, meaning, so if we look at a particular we'll look at some of the alkaline earths. So we'll look at magnesium versus barium. Say, which one would have a lower ionization energy? Notice I could have said higher ionization energy, but which one has the lower first ionization energy? Well, if ionization energy decreases down a column in the periodic table, barium would have the lower first ionization energy. Once you get this and understand the trend arrows, this becomes very elementary. going across a row in the periodic table, ionization energy increases. So if we pick a particular row, so if we have, say, this third row, sodium versus, I don't know, how about chlorine, as far as this goes, which one would have a higher ionization energy? Well, as we follow this trend arrow right here, that increases, the higher first ionization energy would belong to chlorine, as opposed to sodium. Now this makes sense ultimately. If we look at sodium and a metal, metals want to lose electrons in chemical reactions, so it's not that big of a much energy to rip off that first electron to have it become positively charged, because that's a metal. However, if we look at chlorine, that's going the wrong way. Chlorine and any non-metal likes to pick up electrons in chemical reactions, not lose them. So obviously it would be a harder a greater amount of energy needed to strip an electron from chlorine, when it would rather go the other way and pick up an electron. In any event, as long as these trend arrows are adhered to, it becomes an elementary process. So our last trend in the periodic table, that of atomic size, we will address once we describe what is meant by the size of an atom. Typically, atoms are depicted as spheres. And what I have here is a picture of basically a cut through of a sphere, if you will. Now, atoms are mostly empty space, so almost completely empty space. So how do we decide what is the threshold, or where that's the sphere boundary lies? Well, as we know, in an atom we have our nucleus of the atom. In a thin veil around that nucleus exists the atom's electrons, sort of somewhere in a particular area. Anywhere within the circle we see here, we have a non-zero probability of finding an electron, specifically an electron that belongs to that atom. But there does remain a threshold, and remember this is in 3 dimensions, we're dealing with 2 dimensions right here. There's a threshold beyond which there is 0 probability of an electron belonging to that atom existing. So that's what we term this boundary, if you will, of a sphere or a circle depicting atomic size, and that is the benchmark that we will use here. So atomic size with respect to a trend in the periodic table, here is our periodic table right here, and as before in the other 2 we have trend arrows which show this. So again, exactly the same as before, not exactly the same, but the same using these trend arrows. As we go down any column in the periodic table, the sizes of atoms tend to increase. They increase as we go down. So for instance, sodium would be a smaller atom than cesium. Sulfur would be a larger atom than, say, oxygen, and so on and so forth as we move across this. Going across a row in the periodic table, the sizes of atoms tend to decrease across that row. So as we're moving along here on any particular row in the periodic table, each successive element we encounter, their atoms are smaller and smaller and smaller. And there's a number of different ways of looking at this, some that actually make sense, some that don't. By looking at just the S and the P blocks on the periodic table, this trend in atomic size really shows itself. So again, what I've done here is I've taken the S block right here and the P block, which is right here, and gotten rid of the D block, and I've just sort of squished them together. I've done that in a couple of other cases, but that's why we see this periodic table here looking so different. In any event, it really shows itself, this difference in atomic size, as we go down a column in a periodic table. Clearly those atomic sizes increase. As we go across a row in the periodic table, those sizes decrease. Now there's a couple of reasons for this, one of which is more obvious, and one perhaps not as obvious. Let's take a look at another rendition of the S and the P blocks on the periodic table. showing this difference in atomic size. So going down a column in the periodic table, why do the atoms get bigger? Well, there's more stuff there, more electrons, protons, and neutrons as we go from the upper regions to the lower regions. But it's important to look at this more in the sense of our model of where these energy levels, n, remember n equals 1, n equals 2, as we go from n equals 1 to n equals 2 to n equals 3 and so on, they occur at areas further and further from the nucleus. So that makes sense. So potassium here, let's look at an example of, we'll look at lithium. Lithium starts energy level 2, and the boundary of that the atomic size is of the size we see here. Well, the third energy level starts further from the nucleus than does energy level 2. The fourth energy level, potassium, is further out from the nucleus than energy level 3. So it makes sense that, as we go through the number of energy levels and move down this column, then each subsequent energy level is further from the nucleus than the last. So that makes sense. So let's address going across a row in the periodic table. At first, this doesn't make a lot of sense. As I go across a row in the periodic table, at each time, I'm picking up more material. By definition, as I go from sodium to magnesium to aluminum and so on, I'm picking up a proton each time, because remember, as we read the periodic table like lines in the page of a book, I sequentially increase in atomic number. And that is the number of protons. So if we're increasing in bulk and in mass as we move across a row on the periodic table, why are they getting smaller? You'd think with more stuff in it, it'd be getting larger. Well, this harkens back to the concept that an atom is almost all empty space. And to look at this boundary here is almost a fool's errand, because there's really nothing in there to make up that boundary. But what it has to do with the fact that an atom is almost completely empty space makes them squishy. Those boundaries aren't set like the boundaries of a bowling ball. Those boundaries are squishy, like the boundaries, say, of a Nerf ball or something like that, where you can squish it in. Why? Because it's almost completely empty space within an atom. That boundary is really almost arbitrary. But let's see why this is. Now, within a row on the periodic table, we add protons to the nucleus, and electrons are being added to the same energy level. So I have an example here of sodium over on one side of the periodic table in energy level 3, third row, and argon at the other end of the energy level 3 in that third row of the periodic table. Why is sodium larger than argon? Well, it's all to do with opposites attracting. In a sodium atom, what we have are 11 protons in the nucleus and 11 electrons, and canceling each other out. There is actually, because they're opposite charges, there is an attraction there. And that attraction tends to pull those electrons in a little bit because they attract one another. Now, if we go over to the other end with argon, that has 18 protons in its nucleus and 18 electrons. That 18 to 18 is a stronger pull than is 11 to 11. 18 to 18 being a stronger pull squishes that Nerf ball down a little more because, as I said, it's malleable. It is essentially nothing there within there, so we can take that thin veil of electrons, then bring that boundary in a little bit due to that greater force of attraction of 18 electrons to 18 protons versus the weaker attraction of 11 protons to 11 electrons.